Hi all, this is Claude from explicit.com, bringing you a new type of simulation in biomechanics. Let me share my screen firstly. A quick reminder of our website, explicit.com, and here we have gathered in principle, our focus on biomechanics simulations. Today we are going to investigate something similar to this, hip replacement, which is usually made via implanting the femur bone when one of the end, the one which is fused, let's say, or mating into the hip socket, when usually it is destroyed and replaced with an implant. So this being said, let's grab a 3D model. Hopefully we find something very easy on Femur, on grabcad.com. The most used is this one. Everyone and his mother uses this femur, and should use it too. Let's see. I'm a little more interested in this. It looks even nicer. Do we have a step? We have lots of steps here. Come on. Implant plus to lung plus Davin. I think the author is from Southeast Asia. Download. I already liked it. Out of curiosity, let's. It's easiest for this type of simulations. It's easiest, at least in the beginning, to work in explicit dynamics, which is more forgiving regarding contacts and convergence. So this is what I will do, because as a reminder here, we're going to encourage and we want to attract beginners and inexperienced students and engineers. We want to make them like this domain, finite element analysis, simulations, and everything related to that. So let's double click geometry. As space claim will open. Meanwhile, we will take a look here again and see maybe we have another femur. This is a femur, but it has a small hole. I don't know if you see it here. This is not the entire assembly from my experience. It only has this fixture. Let's open this and this one. Also, this one looks nice. All right. Ooh, we have so many 3D models. IGS, it's not so interesting because usually it has faces, it has surface bodies. Here, I don't like this cut. All right, so it's clear that he has made this, let's say, manually in a CAD software. Look here, judging from the. Let's see if we can see it. Can we open it? Yeah, so these are some fillets, and he has done them, let's say, manually. This looks interesting. Open it in 3D, and what do we have? It's pretty realistic. I don't know if this helps us. Because sincerely, I like to have more. I'd love to have smoother surfaces. No. All right, it's nice that we have to choose. This one looks familiar, and yes, download also this one. Do we give a like? I already liked it. And the third option, which is the smoothest one, and it looks very nice. Let's check it a little. So yes, in a few seconds. Yeah, we like it. I like it very much. All right, so now because we have found the needed femurs, all right. Oh, these might pose some problems here. We will see it, how to heal them. So here in library, maybe let's search for hip implant. I don't know how to search it. Implant, is it good? Oh, implant, yes. Maybe I remember from the past. All right. Can I go to search? Implant and holes, too many holes for us in this socket. Maybe this one, because I know that the lattice will not be shown. This is what I know from experience. People do some Voronoi or lattice geometry, and they usually do not. They are not shown in the final 3D model. We will see in a few seconds. Let's see if we have anyone to salute for the stream. Yes, ourselves. Perfect. Do you have a 3D model? Let's see. Let's download it. It's a little too nice for our need. So it's nice work. In here, I would, if there is a lattice, which I doubt, then it will be STL, and it will need lots of healing and editing. Let's see for fun. Ooh, there is the lattice structure, and this will be a killer to make it solid. So let's pass on it. Which one should I use? Maybe this one. All right. This one looks nice. This one looks nice. This one. So, total hip replacement. So I need to assemble them. No way. This is assembly. Let's look a little. By the way, this is how it looks like implanted. Yeah, so there is this hip socket, and usually this part, this head of the femur, gets eroded or fractured. Then it's cut by the orthopedic specialist, by the orthopedist, and this implant is inserted into the femur. Let's look at the difference between the cortical and spongious part of the bone. Yes, so we need to somehow model also with different materials the inside of the femur. Let's see how we will do it. It looks so nice, so clean. So we have also implant files, implant geometries. Let's see also this one. It's a little simplified for my taste. What is the difference between prosthesis and femoral stem? Let's see. This is pretty easy. I mean, simple and easy to use. Like, and this one. He has some. I wanted to say that he has some thin shells, but no, it's not. It's not thin. All right, let's download the entire geometry. So we have ANSYS space claim open. This means we are ready for modeling. Let's start with step files, the ones that I just downloaded. This contains. So when choosing the geometry, you need to look a little at the size. This is pretty complex. It has lots of details, rounds, chamfers, and small holes, and these are very, very simple, let's say. So let's import firstly this femur because it's very light. Yes, I like it. And here the knee joint is, right? So for example, look at one of my most recent models. Yeah, this is the femur, and this is the knee with the missing patella. Patella, I think it's the name. At heart, I'm an automotive engineer, a mechanical engineer. This is why sometimes I don't know by heart the names of all the bones. All right, this is an overview of the anatomy, of the skeletal anatomy. Do we put now the implant? Let's also insert the implant. This one or this one? This one is lighter. It takes less space. we see a collision here, which is not correct. And there is a difference in scale. So the 140 millimeters length is pretty decent and realistic. This means we will need to resize, I think, maybe the femur. Let's resize the femur. Where is the femur? Ah, they are not on the same file, of course. So let's, can I copy this? Copy. And go here and hit paste. Yes. So let's close this file and we'll have this one. All right. At this moment, I'm thinking about how to make this femur with two parts, with the spongious and the cortical side. Let's spongy femur. Boom. Yeah. So let's make it until it's pretty spongy and also empty, kind of empty inside. So what do we do? What should I do? Let's try and keep it empty here on this portion. And see how we can make it spongious. Spongious bone mechanical properties. Not cancerous, I want it spongious. Density, elastic modulus, 0.12. So 3 to 25 less dense than the 3 to 25 times less dense than the cortical bone. So let's try and do something like this. I don't know if it's possible, but let's do it. I will double click to select all faces. I double clicked the entire bone. You know what? Let's copy paste. All right. So copy and paste. Now we have two femurs. All right. We don't have any fear of losing something. Femur and femur. All right, let's hide one of those. We don't need the prosthesis at this moment. Yeah, let's scale this this bone and see what we can do with it. Sincerely, I would like to, in the original femur, I'd like to insert, to overlap a smaller femur. And then I would like to make a cutout between them in order to have the spongious part inside, yes? So let's say pool, we have here the scale command, scale body. I will select this part. A small problem would be guessing the center of scaling. because if it's not exactly at the center of gravity, then we will have an overlap somewhere. If it's not exactly at the center of gravity, if it's here or elsewhere, we'll have an overlap in the initial bigger femur. So we need to meditate a little. Let's do escape. Let's do something like this. It's clear that the center of mass is somewhere here. Let's do our best to select, to create maybe something like an axis here. I selected 2 points. Let's go on sketch mode. I don't know, it's not perfectly defined by only 2 points. Let's create an axis using these 2 points. This is the axis, because once we have an axis, we can insert also a plane. Then I can move the plane. We don't care the orientation of the plane, because I'm going to sketch a point, which will be the reference for the scaling. Sketch mode. So here, yeah, we need to be in the middle, yes? Somewhere in the middle, something like here we need to be. I will click a point, and this hopefully will be a good scaling point. You'll understand in the next minute what I'm talking about. So it is here, curves. Now on this point, I think I can create a point on that point. I think I couldn't create it before because I didn't have a reference. You can create a point on an existing vertex, let's say, yeah, this intersection, for example. Here you can create a point, a reference point. But in the middle, where there is no vertex due to the geometry, we couldn't create a point. Yes, so let me select this point and also select this point. Now it created a reference point. Yes, we have this point from the sketch. I can hide it, no problem. Now it's hidden. Now I have this point, which is in 3D. It's inside, and it could have been a little better. It's skewed to the right due to the. I said the orientation of the plane doesn't matter, but it kind of matters. So undo, 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 undo. Because I would like to undo again, I would like to orient the plane, to orientate the plane with more care. Even though I said before that we're only building a point there. You know what? It's not an exact science. Yeah, I think I'm doing again what I did 2 minutes ago. I would like to measure, if possible, something like this. From here to here. Do we have a distance? No. Come on. 214, all right, millimeter from here to here. Let's check between here and here, 182, as I expected, because I would like to elevate this a little. in principle with 30 millimeters. So here, let me create a point on this axis and move it upwards. I cannot move it too high because it will go here on this bend. Something like this, yeah. So now we have around, let's say, around 200 here and around 200 here. There's a distance between these points. This is kind of, we cannot move it, it's because it's fixed to this axis. So no problem. Let's go to plane view and judging with the IS, judging. Let's make something here. All right. So we don't care about this point. We don't care about this point. I'd like to get out in 3D. Let's see this point. And on this point, which is not very visible, click, let me make this transparent. Now we can see the point, yes? From this point, if I click on it to have a reference to create the reference point in 3D, I can hide this point and we will see this reference. Let's go to what I meant. So he asks for the software asks for the anchor point, which is the point that we just created. Then we'll need to create to select a body, to have a body selection, yes, a solid. So we will write from the right-click show all bodies. We will write a value, maybe 0.9. Yes? Now you understand what I wanted to make, something like this. This is why the reference point is crucial. And it's kind of skewed. So I think what we'll need is to cut the ends and scale them separately. Because scaling the entire body is not beneficial. Knowing that, this is the geometry, yes? Where we are now, I would like to make this portion, I'd like to make it here on the on each end, something like this, all right? Can we open this here? Let's see. Something like this. This is what I'm struggling to make now, and the inside will make it hollow. So this approach is not very happy, let's say. Undo. We need to kind of scratch what I did until now. Let's cut this femur. We already have the plane here. We can hide the prosthesis. Something like here. Let's see if it works. It looks nice. I'm wondering about the problems that this bump will give or not. you know what, let's look at it. Select surface, pull, pull both sides. I wanted to say mid-plane, cut. So these will be the sponges portions, yes? So let's take a look. I would like these to stay opaque, and the femur, let's make this one. Let's make this one transparent. Click, transparent. All right, now we have the upper head. We can call it upper, why not? And this is the lower head. So let's resize them, yes? How do we go inside? We have now the same problem. You know what? Let's do it the easiest way. I will click here and create a point, and I will move this point somewhere in the middle of this head, or in the middle of this end. Move, and let's go something like this, something like this, something like this. And now we are inside the bone here with this point. All right, so we have a very simple reference created. Let's scale it. Scale the upper side. I didn't look at the message. Scale, anchor point. The anchor point is this one. All right, and now we will select upper from here. We can drag it by hand, no problem. Let's drag it a little by hand, but on the opposite side, on the negative side, yes, in order to decrease the scale. This side increases the scale, look here, something like this, and this one decreases the scale, yes? Let's undo, just for you to understand that we need lower than 1 scale, which is logical, yes? While I'm scaling, you'll need to see the collisions that will appear with the original bone. Look here. So let's make it 0.9 would be nice. Even smaller, 0.85. 0.85. Oh, it's kind of too small. You know what? I don't know what scale is this one, but let's leave it. So let's keep the scale. So something like 0.85. I said, all right. Come on. Escape, exit, comment. Look here. This is the problem. This is why I wanted to avoid this problem by using a good reference point for scaling. Because I didn't catch the reference point very well, we will just move this, because here we have lots of space, yes? Let's move it. So now we have an interference here. In the end, we might also be interested in leaving some interference. I said about this bump that it will create some problems. Alright, let's undo a little because I would like to, let's experiment. Yes, we're in the beginning. Let's experiment. Let's scale from below, if possible, yes. Let me create a point on this other point. Now we have 2 points. And move it much lower. You will understand in a few seconds. Yeah, so this is our new point. Let's keep it inside. We don't care about the rotation because it's a simple point. It's not a line or a plane. And let's go further down. Something like this. Okay, it's out of the bone. Something like here. Yeah. So now you are seeing the endeavors, the problems that can appear when modeling such bones in a proper manner. If we want to have separate sponges and cortical, let's say, layers or parts, let's say. So what will happen when we scale from this point the upper side of the femur? Let's see. You see here on the right side we have some collisions in the inside. 0.9. Let's keep it 0. Look here, there are some collisions here. So let's make it 0.85 on the keyboard, and let's see what we have. So I click upper here. Then with move, we will try and position it inside. Let's see. Let's see if it works. This area is not so funny. All right, let's look a little if we have any question from the audience. No question. Here you can see. All right. In 2D, it's very easy to make an offset, let's say, but in 3D, it's not so fun. I think we are slowly approaching something. We have a collision only here. Yes, we're going somewhere. Yes. Yes, but not perfect. the only portion we need to, oh my god. All right. Drag and drop is the game. How do we get rid of this collision? Let's see. Oh, and another one. Can we move it downwards? Let's see. Small collision here and big collision here. All right. So let's drag and drop these axes and I forgot to tell you that we're cutting here. So you know what? We don't need this region. We're saved. So, ladies and gentlemen, we have this plane. Let's cut this head, something like this. Because here we will be inserting the implant, all right? So we're kind of saved because we will not have these regions. So let's cut them. Split body, which one? This one with this one. Delete and split body, this one again, split body, this one with this plane, all right? So here is what we're going to have. You know what, let's save it. This is stream 7 at 9th of January. Femur implant, simply and clearly. All right, we were saved here. Let's see here how we can do this. I am going to scale. First, let's create a point. Yes, something. We can also have a reference outside, it's no problem. Is it in the bone? Yeah, this is in the bone, something like this. And we're going on the pull command, scale. I will select lower and 0.85, I remember, yes? Come on, why don't you work? Pull, scale, pick an anchor point, this one, and click the femur body. Yes, 0.85 I said. Let's see. We will still have collisions. You know what? Let's maybe scale it again with 0.9. So the 0.85 scale, I scaled it again with 0.9. Now we have 0.7 something in principle. Because, I scaled it again in order not to have collisions. So here I will repeat the positioning, something like this. This is the only problematic collision that we have. Can I bring this down? Let's see. With an interference here. Let's move this part here. And let's check if we have any. I think we're on the right track. Only a small collision here. Let's move it a little outwards. This is the problematic area, because when you move one towards, let's say, up, let's say here on this side, this curve will interfere with this curve. So yes. Let's see if we got rid of this collision. Yes. Kind of, yes. You know, anyway, this side, it's not our interest. So we don't care about this side too much. We only cared, let's say, the side, about the side with the implant. Let's make the cutouts. Do it there. Make the cutouts. Move. Yes. Right-click show all, except the prosthesis, which I don't care too much. And let me rotate the plane. I will delete what I don't need. I will rotate the plane so as to make a section view. Something like this. With some minor adjustments. Yeah. So we have something like this. Let's make I would like at this moment to save it as a separate file. Right click, source, internalize all. Now I would like also to save this geometry as let's call it Femur implant v1. This will be like a template before making the combine. After we make the combine, we cannot edit the previous geometry very nicely. So it's nice to have a milestone, like a template, before moving further on. So we have saved this template. Combine. I need to select a target object, is the entire femur, and I will need to cut it with these end parts. Escape. Again, combine. Target will be the entire femur, and I will cut it with this part. Escape. And now some new parts are created. Let's delete them. When we make, when we're going in section view, look here. This is the proper hedge of how they look, okay? So as layer here, by the way, I can hide the ends. These are the ends, I can hide them, and you'll see there are cavities now. Talk about the spongious sides, the spongious ends of the femur. Now what we are going to do is somehow, if possible, unite these cavities, even though they are not cavities. There will be, hopefully we can do as good as possible some cavity from here to here, yes, in order to have this one. So we'll need to model something like a cavity, with an extrude cut. It will not be very precise. Let's now stay only with the femur. Can I for example, with the control press and middle mouse, you can hover, you can cycle the faces, control and middle mouse. For example, it would have been nice if I could somehow drag this and cut, But the problem is, I will show you right now, the problem is that here the section is too big and here we are at the limit. And also it doesn't follow the curvature. When I'm cutting now, I'm cutting about this arrow, which is normal. It has 90 degrees about this plane, yes? Look here, you'll see in exactly 1 second. I forgot to select the, it was selected, the cut command. Middle mouse, with the middle mouse I'm selecting exactly this face, cut, and maybe how much was, I don't know, I will write -300, or -400. Why don't you want to cut? Why? Yeah, so it's not so easy to cut it. Let's propose another way, add no merge, and let's see if we can create something like a kind of a cylinder, all right? Let's see if we can do this. Yeah, this is the cylinder. Should it be 360? I don't know. No. Yes, this is what I wanted you to see. Let's make the femur. I wanted to make, no, this one. Let's make it opaque. Yeah? So this is the problem with that face. When I'm selecting this face, which is the end of the cavity for the spongious bone, when I'm selecting this face, it's not properly aligned with the femur. So let's delete it. And if I'm going to create a sweeping trajectory, let's see, if possible, let's see. Let me copy. Let me copy these faces. This face with Control C, copy, Control V, and you will see it here, yes? This is one face. Let's also copy this face. Control C, Control V, all right? Now, I can hide the femur, and the question is, can I make this thing blend between these two? I don't know, because it will not keep the, it will be straight and my femur is bent, let's say. Let's have it. Failed to construct bend. I think it needs another another face. You know what? Let me see the femur, and let's create a similar section. And if we have, I'm sure that if we have 3 faces, yeah, the start, the middle, and the end of the blend operation, if we have 3 sections, then I think we can successfully make this blend. Because I would like to have a very simplified manner. Let me rotate this with control pressed. If we rotate with control pressed, it will create a copy of the original plane. I will rotate it something like this. Also go somewhere like maybe here. There is a problem with the orientation of this. Yeah, you can see this, the normal of this surface is here, and the normal of this surface is here. So they do not properly, let's say, meet or align, yes, the normals for these 2 faces. It's a little my fault because I cut them pretty random. I didn't foresee the fact that I should keep the orientation, let's say, yes. So this has this angle, let's say 45, and this has this is a steeper angle, yes. They are not perfectly parallel. I would have liked for these faces to be perfectly parallel, but you know, let's hope we can solve it like this. In this plane, I'm going on sketch mode, and here I would like to copy this, to convert this edge. I would like to convert it in my sketch using project sketch. So let's select something like this. Let's see if it works. Yeah, I thought so. It's processing more edges than I needed. Ctrl Z. Can I have an undo? Yes. You know what? Let's double click. Yes, double click because it will propagate the selection if I double click this one. So I have this contour. Now we have the offset command, offset curve, yes? And I can click this face and go a little more inside. There is a gap. This is why you see here there is a gap. This is why it didn't offset so correctly. Let's close this gap in the easiest manner. The easiest manner is this and this. Now let's offset again. There is another interruption or gap. Come on. Why do you do this? You know, let's delete this. And offset it in portions. It has a problem with this side of the offset. Yes, something like this. It's good above 3, okay? So 3.2. Now let's offset the other side. I want to offset this this side. Yes, with Control pressed, we are going to select these edges. 3.2, if I remember. Offset. .2 from the keyboard. Does it work? No. It doesn't easily guess the side of the offset. Come on. 3.2. Yes. We need lots of patience. And 3.2. Come on. Why are you like this? Let's leave it like this. Then we have these two curves. This one and this one. Offset and something like here. Yeah. Oh my god, oh my god, oh my god. 3.2, is it correct? No, let's skip this and maybe make a round. Because we will not be able to join the other ends of the curve that I just wanted to offset. Let's make it like a small radius, something like this. And here the line that I proposed, this line to this end. All right. So let's double click this curve and make it a construction, because I would like to use this contour only. Yes, in principle I should have had a surface here, but it might happen that I have a gap. Yeah, here above. Oh my god, I have a gap here. Can I close it? No. I would be able to close it if I delete this portion. Oh. Yes. And I will assign an arc here. All right. 3D? No, no 3D. Because we have another gap. The question is, where is that gap? Here, not here. Ah. Control Z. Another gap. You know what? Let's create another arc, circle arc, okay? Another gap. Why not? And this is why, ladies and gentlemen, almost no one makes reliable and competent simulations, as they are seen here, due to the amount of work, the tremendous amount of work on making such complex geometries be usable for the FEA. This is why what we offer here is unique and is the result of very hard work. Yeah, and very few people will put in dozens of hours and many days in order to achieve a proper 3D model firstly, then running a reliable FEA. All right, so let's undo again. Let's replace this zone with an arc. Also this, let's delete it. If it's too boring, feel free to skip, to fast forward and look at the final geometry and the final results. I'm showing you the tribulations, the trials of an FEA engineer. So now all things should be in principle good. I don't need these anymore. Let's remove them in order. Here, look. I think it was a forgotten edge there, maybe. Yeah, we have the third surface. Yeah, it's it takes some time. Safe. Let's see if we can create the blend. So I select this, and this, and I will click on the blend operation. It says no. Attempt to blend failed. It can be maybe because they are not parallel. Let's see if we can make them a little more parallel. There is also a problem with how many edges. Ooh, what is this? Yeah, this can be a problem. So when blending, there is a transition made. Let me show if it's possible. Let's see if it's possible to show the transition. Let me show you what I meant. So here, maybe here is easy to understand. So there is a number of nodes or of segments from one side to the other. What I want to say is, if we don't have a similar amount of segments, yeah, from here to here to here, Yeah, this is very straightforward, for example. Yes, on double click, it selected everything, so nice. Here on double click, it selects only one, only this side. Here on double click, it selects without this portion. This means we will have disparate and very isolated segments, let's say. And you know, because I like this pretty much, let's make like a trick and maybe copying it and putting also on the other sides, because we will ensure that we have the same profile, the same surface, and it will be easiest for the blend to appear. When this face or this one or the end one, they differ between their segmentations or the portions of the vertices to be united, then problems will appear. So at this moment, let's kind of hide these two, or maybe delete them because we have the Ctrl-Z command. And let me copy paste this one. Ctrl-Z, Control pressed with Control pressed, yes. And we are going here once, and again I will select this, and with Control pressed we are going here. It's pretty random, yeah, and not in order, but now we are showing the femur, and we will properly orientate these faces, yet, and we will also scale them. Yes, let's scale if possible. Pull, scale, pick an anchor point to scale the body from, and we will select this point and make it 0. How much? 0.8 maybe, yes, or 85. Look here. So we have it like this. Now we're going to insert it, push it inside the femur, inside the bone, something like this. Yeah. So it's too big also. Pull, scale, 0.9, and again 0.9. All right, so it's almost inside. So it's something like this. Let's do the same, almost the same here. We'll drag it inside. Let's scale it with 0.5. I'm selecting vertex 0.8. And I will put it inside. All right. We're kind of where we should be. Yes, something like this. Now we would need maybe to make this closest as possible to this portion. You know what? Let's make it like this, a little inside. Because what I aim to do now, I'm aiming to do a protrusion. It will be like a cylinder, a bent part. We'll then combine it with the femur afterwards. So this is the most correct face. Put here, middle, and something like this. Let's do the blend and confirm if my assumption was correct to have the same face. You see, having the same face ensure the same number of vertices and segments here, here, and here. This was my desire. Yes, let's check it. Yes, save, and now let's show the femur. Yeah, we will have some collision there. Yes. The question kind of is if I can move this part, yes, this part. Can I move it a little downwards in order to get rid of these collisions? Let's see. 1 minute. All right. So do we have any more collisions? Here it's too thin, let's say. It's too thin here. Let's see if I can move it even. No, I cannot move it too much because we have this collision. Oh my God, oh my God. You know what? Let's scale it a little. Yes. .9. Yes. Of course. Control Z is 0.95. Yes. I'm looking for collisions here, especially. Let's move it downwards a little. Yes. 1.5. And let's look. It looks very nice. Now this transition, we can do, save. We can do this transition the easy way and dirty. I mean, just I can extend this face here, and there will be a stepping here, which will not look very nice. Then what I can try and do, another blend here between these two faces. Let's see if it's possible to do the blend, just out of curiosity. So, Control middle mouse, copy paste, Control C, Control V, and here again, middle mouse, copy paste. All right, we have two faces. Let's see if we can make the blend between them. No, it's a segmentation problem, I think, because they have different number of vertices. Yeah, let's just extend this because it will complicate extremely extremely much, very much. It will complicate the geometry, and it's not the purpose of this tutorial. Let me, you know what, let's delete this face. Let me select this, and with cut, I will put until I will cut until I meet this face. So there is this option, up to, control middle mouse, click. Why did I put cut when I wanted just to elongate? Let me just elongate. Pull, no merge. Yes. Up to this face. Control middle mouse. Yeah. So it met that face. All right. Let's do the same here. I already complicated the model and the session, so we don't need to make it a nightmare. Click, no merge, up to, control, middle mouse here. So now let me cut the femur with this this body. Yeah. Let me create another milestone before combining. Femur implant, right-click, source, internalize all. File, save as. Femur implant v2. All right, let me take a look at my smartphone. I have a message, and yes, excuse me for a second. So I replied. Let's combine. I would like this to be the target and this to be the cutter. Yes. It created another part because I don't want to confuse you. Let's exit the command and delete one of these parts. Also delete this part. And now, if we right-click show all, let's see what's in section view. Look here. Yeah. Let me move the plane a little. And maybe rotate it a little, just a little, something like this. Yes, something like this, maybe 2 degrees here. Yes. I click here, then section view. Look here, yeah? So we have the spongious parts, spongious ends, and we have the cortical part of the bone, yes? It kind of, yes, kind of what we see here. Grosso modo, yeah, in principle. It's not perfect. We're making numerical simulations, and then we have approximate models, let's say. So it's perfect like this. Let's take a break for a second and see if there is any message. There is no message. We like silence. And yes. Let's show the processes. I will select these three and call them, move to new component and call everything Femur. Because I would like to hide it. No open but save. And let's deal this a little with the Femur. What's up with this? I've seen already this thing, which is not nice. Let's make a section view. I will click this arc and section mode. This is the section mode. Yeah. So there is a problem with the diameter here, and also there are two parts. What? This portion is not so nice. It's not correct. Ah. He has made a lining. You know what? I don't care about this part. Yeah. Let's change this. One of the radiuses. I don't know which one is. This one is from the outer socket. Let's make it how much? Can I drag and drop? Let's see. Oh, yes. It's too much, of course, but I got an idea about the range. Minus 0.5, I think. But it's not perfectly spherical. It's not perfectly spherical. So what we are doing is something like this. Ctrl Z. Let's leave it like this because I intend to cut it out. Yes. So let's cut this part with this part. Combine, click a target. I would like to cut this one with this one. And maybe delete this small. Yeah. This is a sliver of small shell, a very thin shell inside. Yeah. Right click, show all. Can we look inside? Let's look in a section view. It's easiest if we have two parallel faces. These seem to be parallel. I don't know if they are. Yeah. So this is nice. So this one, in practice, will be attached to the hip bone. Here there will be a spherical joint, or frictionless, maybe with PTFE, polytetrafluoroethane, something like this. Yeah, it's kind of similar to Teflon, which is ensures low friction coefficient between these two, and let's insert them. Let me insert these prostheses here. And 70 degrees, something like this, or maybe 300. 320. 30. All right. And let's kind of align this. something is too big, either the bone, I mean the implant seems too big compared to the bone. And I liked the size of the implant, so let's resize the femur. Let's resize it to make it bigger in order to properly fit this part into this part and vice versa. All right, so pull, pick an anchor point, maybe from here, and I will select the entire femur. This is the femur. Is it possible to scale it? No. Why should it be possible to be so easy? Come on. Escape, pull, pick an anchor point. Come on, pick an anchor point. Select bodies, all right? So now with coming from the right side, I will select these three bodies. And how much should I make? 1.1? 1.1 again. Yeah. 1.2. 1.1 again. I would like this width, this thickness, let's say, to be kind of the same as what we have here. 1.1, and we're set. All right. So let's see if we can kind of right-click, source, internalize all files, save as version 3. Let me rotate it a little, just a little, something like this. Done. Something like this. Something like this. Oh, it looks so nice. You know what? Let's kind of stop here if possible. Yes. So, do I care about these radiuses? You know what? Let's leave them, but I hope they will not create any problems. I'm talking about these remnants of filets. Control S. All right, what do we need to do? I need to combine this with this. And I will delete this thing from inside here. Even though you don't see it very nicely, you can see that this portion, yes? This portion is gone. So look here. This is a very light pink. Yeah? Or this one. I can click here. Yeah? This is the portion that should be removed. Escape, and in section view, let's make a section view to encompass also the femur and the implant. something like this. Yes, something like. If we didn't catch the look here, so this is how it looks like. Now we have, if we leave this, we have a lack of realism, let's say, yes, because this is part of this one, and this should not exist because the implant came afterwards. So in order to solve this, you see, look here. There is this portion of the bone. This portion of the bone cannot exist, all right? This cavity can exist, but not this protrusion. So how we solve it? Control Z, and I will remove, hide others. I will remove this this one because it creates problems during the combine command. Yeah, it ruins the realism. Right click, show all. Let me combine again. I think I need to undo. Yeah. Yes. So I need this to not have this cavity. Let's see if I can somehow select this cavity and delete it. Can we? Delete? Yes. Show. So let me now hide others, remove this cavity in order not to ruin the realism. Combine here, here, and click this extra part, yes? If there is an extra part. All right. We check everything. I don't care about the plane at this moment because we have this curve. Having this curve, section mode, and look here, yes? It looks awesome. So my intention is to fix this outer face and rotate a little the femur, okay? Or should I press it? I will see. When I rotate, it's not so very tremendous or spectacular, but when I press here, it's very nice. I will see what normally I would kind of wanted to show the spherical joint here, how it behaves. All right. Whew. What have we here? We have kind of a cut in the bone here. I didn't see it until now. We have a cut in the bone. Let's make the bone opaque in order to. The bone is a little hollow here. What can we do at this moment? It's not a hole that we can heal. Look here, prepare, repair missing faces. It's not a hole, no areas found, yes? It's not a modeling defect, let's say. It's just a concept misjudgment, let's say. It's an overlook. let's see what can we do. For fun, just for fun. I'm wondering, there is this command, if I click two faces, these two faces. If I click detach, then the entire body will become two different surfaces. One surface is the pair that I selected for detachment, and one is the rest of the femur, yes? Look here. So these are the two faces, and this is the rest of the femur. Yeah, something like this. What I would like to do is to force the software to heal this hole. Let's see if it's possible. The problem is that we have two holes. I have a hole here. Let's see, missing faces. I have a hole here, but it does not get this edge. So if I click here, it is kind of healed, but we're not convinced until we heal the other face, yes? This one. So this is the bone without any hole. Only I think we have a small problem. Let me show where the small problem can be. So I'm orienting for you to see the hole, how it's being healed by the software. So look here, yeah. The problem is like this. Control Z, Control Z. The problem is when healing, Control Z, when healing, these faces are so close apart. This one, yeah? This one is so close apart with this hole, this remaining hole, that this one kind of overlaps with this face. And it creates problems. Because it's not so important for us at this moment. Let me try something like, let's go back to what we have. This one, yes? Keeping the orientation of the plane, let's see if we can kind of cut the femur a little. Just let's see if we can cut it a little. And maybe blend the ends. Let's see if it's possible. If it's not possible, we'll leave it like this. And we'll take it as an oversight because it's not important for our example. And we can pretend that an artillery project raised the bone. It's kind of touched, just passed by, just we do what we want to do, yes? Let's split body with these two planes. I will delete this portion, escape, and let's see if we can make the, oh my god. Let's see if we can make this blend that I wanted. I will click this face, also this face, and try and bend it. Let's see if it works. There are portions being too thin, and we're kind of demanding too much from the software. Maybe I need to remake the cut. I need to extend a little the cut portion. I mean, I need to enlarge the distance between the planes, the cutting planes, in order to have a thicker contour. It might happen that the software will freeze, and I will need to close it, and we will revert to the last saved version. You remember where you saved with version 3. Yeah, I think it's kind of too much for this software. Let's see. I'm looking at the number of usually when it's freezing, it takes up all the cores. It occupies all of them, but because it's using only 2, 3, 4 cores, it's pretty optimistic. So do we have any message? No. Okay. What is the time? How much? Almost hours. All right. I so not like to close the software. You know what? Let's leave it at least 1-2 minutes and go to other people. ANSYS Femur. Everyone has simulated. Look here, the Spongy side, yes, but she used only. Almost everyone uses only one portion, yes. Here, ooh, this looks nice because he has done the cutout, yes. Oh my god, I think it's not funny what is here. Weird. Are we in luck? What is this? Here there is something. Ah, the software made the same problem as before. You know what? Let's make what I suggested. Let's increase this distance. Firstly, let's see in transparency how much I am going. Something like this. I would like to ensure that I don't have this small area here, yes, this thinness. Instead, I would like to ensure such a blend. You'll understand in a few seconds. Split body, this one, with the two planes, right? This one, and now I have more space here. It's much thicker than we had before. I'm talking about regarding the blending. I would say it's much thicker, but yeah, let's see. Let's see if it's like this. Maybe it's just wishful thinking. Mm. Let me orient this something like this. And let's use the same plane. Control pressed. With control pressed, we're going here. Let's split this body with this plane. And yeah, let's see. We are not so much in luck at this moment. If I exaggerate and move the plane even further, I think the blend will not look nice if there will be a blend in the end. Come on. If I copy paste, then move this to here, does it help? Let's see. Maybe not. or maybe yes. So in this live stream, you have seen various types of operations to use when we encounter some geometry problems. And we need creativity and to come up with new ideas and yeah, escape. Let's make this opaque. And yes, it looks very nice. I think we need to join it. This is one end, this is one end. All right. And this is a surface. What can we do with this surface? Hide others. This is a surface. How is this a surface? Usually when we see opaque bodies like this, they are usually solids. But at one point I made it opaque. And let's go here on repair and see how we can solve it. Yes. Maybe there are some problems. Usually, the easiest way is to go on missing faces. There are no missing faces. Gaps. Two gaps. There are two gaps here. Now it's a solid, all right? Perfect. Right-click, show all, and I am going to unite. Yeah. Let's make it again transparent. Yeah. Let's unite them. Save. I will unite this. Control press this. Come on, unite it. Merge it together. Session 12, biomechanical. So pretty coarse mesh. The bone is only 20 centimeters, 30 centimeters. We can say it's a child bone, all right. Safety factor, force, moment, and fixed support. This is all right. Femur bone static. Fixed time pressure. Come on. Hello. She has modeled. If she did the model, she has modeled by hand. Yeah. It's not very immersive, let's say. Look, they are united, and the third one is this one. With control pressed, yes? She shows in X-ray how the bone looks like, looks like in reality. And she is applying frictionless support. Yeah, because this is the socket, hip socket. Of force and some values. Miss Heidi. All right. Nice work. what is this? I was in engineering, one of the top companies, top collaborators of ANSYS. I advise you to watch this this scenario because it tells very much about what occurs. It's talking about segmentation from computer tomography into mesh, into cloud points, into ESTL, into, I think they are talking about this, and how simulation can be used. Yes. These types of models, let me show which one. These are usually taken from anybody. The software anybody, yes, so anybody. Something like this. This software is, let's say, it's the top of the art, state of the art at this moment for biomechanics, kinematics. 1 second, let's ensure that we have a femur. I think we have a femur. Escape and save. Right click, delete empty components, and we have, we have a femur finally with no errors. We can ensure that there are no errors by looking a little in the section view. Let's look a little here. Look how thick it is, and yes, we overcome this. I thought it would have been much more problematic. Oh my god! Oh my god! Let me save this as Femur Implant. We have a 3D model. Let me copy the naming. Copy. Then paste it here. All right. Next thing, following engineering data. We need the material for the implant. We don't care about steel, and for the bone. The implant is usually made with titanium alloy steel. I will not insist too much on this. Only that I would like to be nonlinear. Always in explicit dynamics we use nonlinear materials. This is my advice. Then let's kind of create the bones. Yes, the bones materials. Do we have, just for fun, do I have some bone export? Yeah, we have. I have a bone nonlinear here. Should we use it or not? Let me import it, and I will look a little on it. I would like to see the properties. So, at this moment, we are going on internet, and bone property. Let's see the mechanical properties for each one. Properties, and it says something like this: cancellous bone 0.4, 0.3, and the cortical around 12, and some shear modulus. Yes? So let's see if we are right here. We don't have any density. Cancellous bond, 330, 831, 0.7. You know what? Or trabecular bond, all right. Toughness. Ooh, is this good? Cortical bone. Cancellous bone. I would like to see the density. I would like to see the density. Let's keep the nonlinear thing. I will put it in the end. In here, because I don't like the word cancellous, I will write spongious bone nonlinear. All right, and here maybe 500. Elastic modulus maybe 1000. Poisson ratio 0.35. And I have assigned some tangent modulus, so feel free to also produce something like this. Heel strength, spongious bone, heel stress. Do we have a heel stress for the spongy bone? Yeah, it can be. Oh, so much lower. Heel stress, look here, 50. So let's make it 50. 50 and do we have a tangent modulus formula calculator? Let's see. Come on, give me a calculator, please. Let's see if I have what is tangent modulus. How can I get a tangent modulus? All right, let's spongy bone. Can I ask for a tangent modulus? Let's see. Tangent modulus. Can I? Do I dare to ask for a tangent modulus? Elastic, yes, modulus. Yeah, I know it. In many finite elements motor, the tangent modulus is said to be 5% of the elastic modulus. The problem is that this is the Young's modulus. Yes, this one, the elastic modulus. And he said 5% of 1000, which is 50. And here, this value is nice to me. I like it. So let's use 42. We need to think before adopting what AI says. This is spongious bone nonlinear. Duplicate. Let's make it cortical bone nonlinear. nonlinear. The images, cortical bone. We have Young's modulus around here 17 gigapascals. In our case, I'll put 16 to be more original. Do we have Poisson ratio? We have 0.4, 0.25. It's orthotropically defined here. Poisson ratio, look here, 0.3. All right, we'll leave it 0.3. 0.3. And yield strength, cortical bone. We have the yield here around 170 maybe, 170, and the tangent modulus should be cortical bone tangent modulus. It should be, I don't know, 1/200. Elastic range, post-yield, bilinear response under 3%, but no tangent modulus. Come on. Then I think we will percent maybe. Cortical bone tangent modulus. All right. Do we dare to find out? Do we dare to find out? There was this website, ResearchGate, and here maybe, do I have an account? 6-digit code, all right. I will unshare the screen for a second. And share it again. Cortical bone tangent modulus. Cortical bone tangent modulus. Please search on ResearchGate. Elastic modulus, come on. Of the PT. Young moduli, share moduli, increasing tangent modulus with implantation. Yes, compressive strength, method of determination modulus. All right, so please give me values. Elongation load, length. What? Come on, Control F. Can I search tangent of the P substance Similar findings were obtained for the BTBP graph, but no values. Tangent modulus. Oh, look here. Yes. 900? Yeah. 900. I was thinking about 10% of the Young's modulus, and yeah, it's nice. I like it. Titanium alloy nonlinear. Should we keep it with two materials? No, let's not complicate things too much. Because we're addressing beginners and we want everyone to be in shape. Hello, Mr. Vasile. Thank you for the chosen team and concessional general of the solving team. Thank you, Mr. Vasile. Thank you. I learned a lot from watching this tutorial. Mulțumesc frumos. Please write in English, all right? So even though the model is not anatomically correct, of course it's not. It's taken from GrabCAD, then heavily edited. Maybe it would have been nice to continue with the simulation, boundary conditions, and have results. This is the purpose of the simulation. So this is what I will be doing in the next minutes, okay? So it's just a tutorial. We are here to learn the basic principles, some modeling, some healing, meshing, results. So this is the purpose of this live stream. So thank you for the appreciation, and please let's continue discussion in English because we want everyone to understand. Yes. All right. So thank you again for the appreciation. The geometry is being loaded now. It's not academy here. We're not at a lecture. It's not a paid lecture, a classical course and training with examination, and it's something I would say basic, even though it's not basic, because not many people do what I do. I'm talking about these simulations, not many. I think I would consider them basic, and very few little people think they're basic. They are not so basic, but I want to keep things very clear, very simple to attract, as I said before, to attract more people to this simulation, more young engineers and students. All right, let's save this. It's a lot of work. It is a lot of work. So this I will say, implant, I don't know what. This one will be implant socket, even though we were going to use the same material. This is upper spongy, and this is the lower sponge, I think. Inside here, look, this is the lower sponge. All right. And this is right-click show all bodies. This is the whole femur, which was cut in order to accommodate the implant. Femur. We said that we're going to use cortical bone for the femur. For the lower and upper spongy, as the name says, spongious bone, nonlinear. Implant and rod, let's use titanium alloy nonlinear. All right. We have some contacts here. we have some contacts here. Now I have to make a decision. Do I complicate the model or not? You know what? Let's do it. Let's do it. Maybe 2 cases. All right. I would like to suppress all these in order for you to see some new options. All right. One option that I would like you to see is this one. Let's use body interaction bonded. Yeah, let's hide this, hide body, and let's use body interaction between all these parts. Control B to select body, Control A between all these parts. Let's make them bonded. In order to ensure very well touching of the nodes, let's assign like a pinball radius, an offset. Yeah, let's assign. How much should it be? Maybe, I don't know, 1 millimeter, maybe 1 millimeter, right? We don't want 2 because 2 is somewhere is the thickness. Look here. 2 can be the thickness of the cortical portion. Maybe smaller. This is 1, something like this. All right. Maybe we can use also 0.25, very small. All right. What we have here? So we have this one interacts frictionless with this part because of the default. Yes, we can delete the default. We can customize as we want. Let's make here. Let's fix this side. Control F to select the face. Let's fix it. Why? Because I would like to create body spherical. Yes, this one is spherical. I would like to select these 2 faces for one side, and this one inside or this face. But I would not like to select this one at this moment because it was fixed and I don't want to create a confusion. Yes, so in order to be very clear, I would like to select these faces for the reference side. Yes, right click, show all, and we have this spherical joint. Now let's see what we can do with this joint. Maybe rotate this a little. Yes, let's rotate it a little according to this spherical joint. This means we will create a revolute joint here, body ground revolute joint according to this. I will kind of scope these faces. Yes, Control F. For the selection filter, find box select. Yes, I made it so complicated and confusing in order to edit this reference coordinate system. Look here. So sincerely, I would like to have the z-axis, which is the rotation axis. The rotation axis is z. Yes, we all know. I would like to have the z-axis collinear to the y-axis, the absolute y-axis. So the z relative or from the reference to be collinear with the absolute y-axis. The easiest way is to make something like this. Yeah, and this will be the rotation. But the rotation occurs here, while I would like the rotation to be somewhere like here. All right. This means I would want to move the coordinate system. Yeah, not the joint, not the revolute joint. I will not interfere with these faces. I would interfere with the reference. This means I will select here. Yeah. Mode, single select, and I would like to rotate about this sphere. Yes. So let's click these two faces, and this coordinate system will jump here. Yes, we will rotate according to this. Let's see. I think it will not be very spectacular. The results will not show too much stress. Maybe because we have perfect touching here due to the spherical joint. It's not a proper contact here. So at this moment, this body interaction is somehow redundant, because it's not a touching. There is no touching here due to this spherical joint. The joints are defined by the mass centers, let's say, or the geometrical centers of the parts. So the software scopes the center of this sphere, and kind of aligns it with this center, even though they're the same, okay? But they will not touch. Yeah, usually. When heavy contacts, they will not touch. Let's see further what will occur. I'm giving extensive explanations because I kind of know how the software thinks. Capture curvature, no. Quality, low. And let me save it. Let's give it a default generated mesh. Oh, super. 1000 and super. Let's also, we have a green checklist. Let's create a section view. How do we want to create it? How do you want to create this? Something like here, I want to encompass everything. Section planes, new section plane. Something like this, yes. All right, now let's refine the mesh. We have multiple methods to refine the mesh. Here, instead of 19, what will occur if we make it 10? Oh, so nice. I'm looking here because I see something. Ah, it's the stepping, yeah, but it went pretty well. We don't care too much. Now I'm wondering if we should make it much finer. Just a little finer. Yeah, you know what? We're mostly interested in. I'm interested in seeing how much the solving takes. This is why I will not refine too much right now. Let's assign a very fast solving end time. Here, I would like to make this no and output control 100, number of points. All right, let's assign the joint load. Loads joint, the rotational joint. I would like to go on upper on this direction, yes? Rotation, tabular time. How much should we go up? How much should we go up? 30 degrees or 45? Why not? With minus, because I would like it to go up, yes? Something like this. Even though this arrow is not properly positioned here, it should be here at the reference coordinate system. This arrow should be pointed here, yes? But maybe they left it for everyone to understand. We have the loads because we have defined the joints here, all right? We have defined the boundary conditions. Deformation, velocity, strain. Sincerely, I don't need the velocity because it will be kind of high due to the very short in time. But what I can do is to have force reaction. Joint, force reaction maybe in revolute, and force reaction in fixed, why not? And also in the spherical here. Spherical. All right. Regarding solution information, equivalent stress total deformation, right click, switch to automatic mode, save. And let's make it here 8 cores. Let's solve. Let's get an idea about the solving time. Do we have any more questions or reply? Okay, even if the mode is not on, it might be better to continue exactly what I said. Yes, introducing the conditions. Yes. Yes, sir. Where are we? Here. Everything is nice. So, we seem to have a small problem somewhere. And at this moment, we cannot see where the problem is. I can make this 0 just to see if we can overpass the, if we can overcome the error. Oh my God, I didn't put my microphone here. Oh my God. Oh, I'm sorry. I hope I didn't ruin the live. Oh my God. Can someone tell me if you heard me until now? I have 2 spectators. Can you please write in chat if you heard me? Even though increasing the sound volume. So we have 13 hours to wait, which we will not do, of course, but to have a feeling, all right? All right, let's interrupt it. Can someone please tell me about the sound volume, if it worked or not? Maybe the sound worked because also the webcam has a microphone. I will see. Let's close space claim. This is like a template, all right? So because it works, we'll not touch it, okay? Maybe we can write 11 hours of solving. Save, duplicate. We can, thank you very much. This is a good news for me, because for a second I thought maybe the sound ruined everything, but yeah, thank you much. Thank you much. Thank you much, Mr. Basile. Small question, are you from the Technical University in Iași, Romania? Is it from there that I know you? Or I'm sorry, that you know me? Let's watch a second. I think yes. I think yes. You please confirm if this is you and your company. This would be nice to get to know each other. All right. So we had around 11 hours of solving, which is not so funny. What do we do in this situation? We can make the mesh coarser. Let's make it coarser at this moment, all right? Or not. Let's not. We're going to decrease the end time, even though it's not realistic, all right? I'm solving with 8 cores. A hospital, a laboratory, a company should solve with at least 64, 120, 256 cores. So, yeah, more realistic end time should be used. Okay, yes, perfect. Thank you for the understanding. If I divide it with 10, then we will have 1 hour of solving, and we also don't want to wait 1 hour. Let's modify again here, -35. Let's make here 10 again. And let's see now, we have around 1 hour, all right? Let's see if we can make it maybe around 30 minutes, and we can watch together some examples, some videos made by other people. 5,000, all right. Clear generated data, yes. from Galatz, from a little south. Yes. Nice meeting you. Nice meeting you, sir. I'm a Claudio from Iași, Northeast. Yes, Iași. I graduated Faculty of Mechanics and CMMI, Faculty of Machine Manufacturing. Yes. All right. So. One hour is predicted. Let's pause it because I want to make it half an hour, maybe 20 minutes. All right, and we're cutting lots of corners in order to do this. There will be a problem. There will be a problem if I decrease the end time too much. There will be a problem because we will have a shock. You can already see this portion where the rotational joint is applied is already being displayed too much. And we might have a shock. We might have a shock. Yes. So performing this rotational movement in explicit dynamics where time matters, maybe it's not such a happy thing to do live because it takes too much time, being forced to use higher end time. You know what? Let's move this simulation to a static simulation. Yes. Because we're here, you know what? Because we're here, I can suppress this revolute joint. And of course, that I can apply a pressure. Where are we fixed? We're fixed here. Let's suppress. Let's fix it here. Hide all other bodies. As many of the people do. Home. All right, so we have fixed here. Let's delete this. Let's press with something, you know. With this, let's press with the socket, with the cap. With the force. Home mode, selection mode, single. Apply. And we will compress it something like this on the -z. Not vector, but components, yes? -z minus how much? So a person is, let's say, 70, 80 kilograms, 800 newtons. We split it in two, 400 newtons per leg, yes? 400 with minus. Yes, and we have this. This is a very simple scenario. Then I will attempt to make it also, to make a rotation in the static if we have the time. Why I'm leaving these joints? Because I would like to convert this simulation in a static structure. So I'll leave these joints. At this moment, because I know it takes 1 hour, let's make the interaction between now the interaction between these two is frictionless. This means if I press with the force here, it will come out. It will get out of here, all right? So let's make this contact. Or maybe show it, how it gets out. It gets out, yes. Let's show how it gets out. We have 1 hour. Do of solving. Can I help it with something? Let's see if it works. I wanted to say here -9, E1 and -9. Maybe some mass scaling, I don't know if it works, maybe it will not work because we don't have linear materials. Let's see. We can be optimistic nevertheless. Fraction of mass, oh, it's adding, perfect. 50. You can revert to the previous explicit dynamics simulation that I made in a previous live stream where I explained the philosophy of mass scaling, which helps with faster solving by increasing artificially the density of some elements. This has frozen here, it will not work. Show me the solving, show me. It might be that yes, here. Some executables remain open, so they need to be killed manually. Or stopped manually, because it sounds much nicer. All right, so 150 it is. Clear generated data, yes. I really need the mass scaling to decrease the solving time. How time does almost 3 hours. Cross power faculty. Yes, sir. Material science. Perfect. We are engineers. Nobody's perfect. What do you say? 7 minutes, come on. It's America, it's America. Someone should make a short, a clip or something. 7 minutes instead of the initial 14 hours. Yes. All right. Where were we? I will close these and look at other people's simulation. I was talking about the Anybody software, which is the state of the art for biomechanics kinematics, let's say. And implants, composite draping. No. What is this? 360 past. From 13 years ago. This is a dedication for Arya Prihutama, Mr. Friedrich Piotr. So what I know is that since recently, YouTube is kind of letting AI resize, re-edit, re-post the movies. This is why what you have here, while it looked noisier and low resolution a few years ago, now it looks like this, in almost incomprehensible regarding text, because I know that AI has begun to modify this. Oh, 4 years ago. Oh, yes, and he takes only fixed and pressure, static structure. Yeah. It's nice, it's simple and nice. Mr. Friedrich Piotr again. He's doing a model simulation. Let's see some animation. Fixed and pressure, yes. ANSYS workbench femur bone structure analysis. Does this work? Yes. Oh my god. With control pressed, he's selecting this. Why don't you know about Windows selection? Come on. Press control button pick or pressurize. The same pressure and fixed support. YouTube. Can I make bone here? Bone? The same bone. Let's see something more complex from my part. There are two cases, yes, one without, so the vertebra is fractured here without any support, any implants, and here we have the spinal fusion bolts and pins. This is something more complex. It was a lot of work, and we have realistic materials for these cartilaginous, for these cartilages between the vertebrae. How is spelled? Cartilaginous. Cartilaginous. All right, cartilaginous. Nice. So, what? Let's see. People from Dynamo, one of the top is there. They're using top LS Dyna, and they're there with alongside CutFem and others. Yes, they are the top. This was nice. This is a simulation for Halloween. Firstly, it's a drop test. Yes. Yes. Frictionless supports, no frictionless body interactions, no contacts, an initial velocity or a displacement from the pumpkin. Yeah, it's very cute and very nice. And Dynamore, yes, they are the top of the top. Improve safety performance with Hans and design. Hans, I think, is the dummy. I think I should do something similar. Only touching such a 3D model is not so easy. Let me show you what I'm talking about. So, for biomechanics, the state of the art, the standard, everything, the top is this one. It's the TOMS. The TOMS. Total human model for safety. Of course, you cannot download it. I think, yes. Only, yeah. I wonder if they are giving this to students. About. Look here, yeah. So this is in principle, the model that Dynamore is using. Dynamore is using the TOMS model. I think, maybe, let me see if they have a Hans model. More about Hans. This is from ANSYS. Hans is a sophisticated tool used across various fields to simulate and analyze the human body response under impact loads. It enhances safety, performance, and design through detailed digital representations and simulations. So it's a tool. Anatomical accuracy, physiological functions, mechanical properties. Visual applications. Applications of what? No. So Hans is a tool? I thought it was a model. Yeah. You know what? They are taking this model, and just it's a drop test, yes, of this model. So yeah, it's very simplified here. A drop test. It's a drop test. Nevertheless, yes, a lot of work. This is Hans. Oh. What have we here? We have results. Let's see the results. It's just a force. Yes, let's copy here with 10 maybe, and we have results. Let's remove the edges and animate. It's a real scale. This is why the bone does not dilate too much, because 40 kilograms is kind of realistic. Let's go in section view and see. Oh, yes. It's nice. I don't want to exaggerate it too much. This is only for principle, right? Just for fun, let's give it an auto scale. Okay. These, ladies and gentlemen, is let's say it's a draft. It's a basic simulation in explicit dynamics. Let's 7.5 minutes. Nice. Let's duplicate this. Do we have any question? Cross-border faculty. Okay, it's the same. We're here. Tombs. Yes. So Tombs is very detailed. It has the entire skeleton and almost all the organs, or maybe all the organs. Yes. It was a lot of work on doing this, and I think you can get your hands on it if you ask from the faculty, from the academy, from you can get your hands of it if you're a student. Ooh, so nice. This will give me ideas for future simulations. Let's convert this to static, and let's see if we can make that rotation that I was talking about. Convert to static. Can I animate this? Oh my god, even the hood, and oh my god, this is Nirvana, simulation Nirvana. All right, so Tombs model is the most realistic one. It converted to static structural. Let me show you how to perform the conversion and draw your attention towards where we need to look. Firstly, we need to remember that the mesh in explicit is linear. So either we make it quadratic or program controlled. Program controlled will make it quadratic, with mid-side nodes. Here on the sizing, let's see, yes, it kept the sizing, all right. Now, right-click Generate Mesh. It's another story. All right, when we have such problematic geometry, because these facets impose some errors, these ones, what I like to do, and I advise you also to do, home, model, virtual topology. In here, maybe change it to medium. It will unite many of the faces, and it will kind of heal some of the problematic features. Right-click, generate virtual cells. here, and also inside it generated. Yeah, it united, made many of the surfaces, it united them. Let's again create generate mesh, and let's see where the problems are. Maybe the problem is with the sizing. What happens if we hit 5 here? Ooh. Ooh. Let's go with 7, and here instead of use adaptive sizing, let's make it yes. Here this is possible, this is not possible. Span angle center medium, does it help? No. Let's go for defeaturing if possible. How much? 0.5? And transition instead of slow, let's make it fast. We're going somewhere. We are going somewhere. Yes. Instead of 0.1, instead, can I make 1 here? Maybe 5 millimeters here. No. So 0.1. Shortly, let's change it to no adaptive sizing. Very quickly, let's see. Yes, again, mesh defeaturing, yes. At one given moment, there was transition slow. Come on. Mesh. What happens if we assign 20 millimeters or 12 millimeters? Nothing. Check mesh quality. Can I hit no here? Smoothing. What about smoothing medium? Ooh, yes. So we have two parts that are not meshed, this one and this one. All right, let's duplicate this. So you have seen the philosophy changed, the paradigm changed. Firstly in the mesh, then you will see this change in the contacts. Any more questions? No more questions. All right. So let's assign a sizing. Control B here. Let's make it, I don't know, 4. Let's make both 4 and see what will happen. So this works with 4, all right? So we will leave it like this. Now the last body sizing is the femur. How much should it be? Maybe 3 millimeters. It has some steppings. It has some sudden changes into profile, and so this is why it can happen that it has some problematic features. And the explicit dynamics is much more forgiving in this regard. All right, then instead of exaggerating there, let's go with 4 millimeters and make a defeature. Firstly, 0.1. Behavior. Let's make it hard. Zero 0.3. And 0.6. Come on, come on. Let's go to no here. Use adaptive sizing now. Oh. Oh, we have a defeature already. So this means what I'm doing here, it makes not much sense. Can I defeature with 1? Or will this defeature size overlap the other one? Let's see. Whew. Finally, only we have a very coarse mesh. Let's close this. I will delete this and I will duplicate this. This will be like a template. So we have a high. We have a high from someone. Hi. Yes. Here, static structural. Just bear with me a few more minutes, and we will solve it nicely. You'll see. So we have the mesh finally. What do we do to make this mesh much more coarse? Let's attempt a 6 millimeter mesh. What about a 5 millimeter mesh? With 4 it works. Let's test with 10. No. So 4 and 1 works. Can we test with 6 and 1.5? For people just joining, we are... Oh, yes. Whew. We have a nice mesh now. Save. Let's see for the implant rod here. Instead of 4, can I make it 5? Yes. Save. Finally, we have something nice. You know what? Excuse my paranoia, but I will delete this previous template and I will duplicate this one. Oh my god, so many obstacles, but we overcome them all. Hi. So what I want to do is to rotate the femur around the spherical joint of the implant. And I would like to do this in static structure. So we have the mesh. Now let's assign the contacts. You know what? Let's unsuppress these contacts. The body interactions disappeared. Right click, rename based on definition. And implant rod to implant socket. Bonded. No. this should be suppressed because we have this joint. We have this joint, the spherical joint, yes? Implant rod to upper spongy. What? Ah, only one face? Why don't we have more? Let's have more faces. Selection, adjacent, and it took everything. All right, apply. And here also click, and instead of one face, let's go to adjacent. Yes, apply. This is a properly assigned contact. Bonded. The femur and all right, you know what? Let's make this connection if it works. I don't know if it works. At least limits. Okay, limits. Apply. And here again, not only a few faces, but more faces, yes? Adjacent, adjacent, apply. Look here, how nice it looks. Bonded. Also here, yes? Adjacent, adjacent, apply. And here, adjacent, adjacent, yes, apply. We have proper contacts. Joints fixed, this one is fixed. This one spherical, this one revolute. All right, let's unsuppress the revolution joint. I will delete this because we don't need. And we will apply the rotation. Now we can see that the rotation due to having a different meshing now, because we apply the virtual topology, we need to kind of remake these joints. Let's look a little on that. So this one is good. This one is good. Only this one. We should take more, yes. So here, home mode view box select. Let's take. It takes faces which were left from the virtual topology. The virtual topology imposed these faces now. And this might look like a problem, but it's not necessarily a problem. Let's do it the easiest way. Mode, single select. I will select a face here and propagate it using here, selection adjacent. All right, I don't need this. With control, I will remove them, and here, apply. Let's see how the reference looks like. Perfect. This is the correct reference. All right, we have everything now. Let's make 2 steps in order to refine the rotational joint. Large deflection on, and the solver should be direct. Rotational joint, I said minus 17.5 and minus 35, yes? This is what I said. Yes. Let's see what gives. Now I can use more cores. 500 is a wishful thinking, maybe in the next years. Maybe, surely in the next years. Do we have everything? Yes. Yes, no mass scaling here, no mesh erosion. different mesh settings, different contact settings, impact settings. The joints remain the same, only the virtual topology changed the scoping of the boundary conditions, let's say. Let's see how fast it goes. It's kind of slow. Oh. Let's see if it works. If it will work, I don't know. Eventually it will solve, but I would like to obtain results, decent results during this live stream, not offline. Let's see if it works. It will work. Let's assign very quickly some time steps. Let's begin with 12. Maybe it's too much for the solver. I like time, and here carry over time step on 0.1, 0.025, 0.1. Let's see. Clear generated data solve. Clear generated data solve. And again. All right, let's look on, this is Dynamo, yes. Lots of awesome simulations. Let's Dynamo. I think Dynamo is now part of ANSYS and Synopsys, I think, maybe. This is Hans Viva, Tooms, Piper. So Hans is not Tooms? Is it possible? Agenda. So I understand that Hans is a new model. It looks much nicer than the Tooms model. So it's a model made by, owned by ANSYS? Only tensile region, of course. so hard to simulate on NASA. The results in figure tombs in body parts of the reef are open. Tombs. So are these tombs or not? It goes nowhere. All right, so let's not wait a few days. Let's force some solving. Hans model is mostly finished, so it's another model if I understand. Yeah, it might be. It might be a model different from tombs. So this is what we're going to do. Yes. So we're going to enforce some stabilization, yes? This normally should should increase the possibility of convergence. This is only for disparate measures because we want to achieve results now, but it shouldn't be used in practice. So one of my, or maybe the most viewed simulation of mine, almost 400,000 views. It's a simplistic model that I took and mixed and combined and overlapped and tweaked and edited and customized and so much more. Yeah. It was a lot of work. As simple as it looks, maybe it looks simple, it was a lot of work. Why doesn't it work? It should work. Is this too much? Maybe the rotation is too much. Minus 5, minus 10. How long are we talking about? 334. Okay. So, maybe we need to refine some mesh, maybe. Where do we have coarse mesh? This is a coarse mesh, this one. And somewhere. These also are pretty coarse. Of course, some femur. Why? Let's change the scope of this revolute only to these faces. Only these two faces. Or yes, something like this. Clear generated data, yes, solve. Clear generated data, yes, solve. Again. There is a problem with this revolute joint. I don't know why. This is correct. This is correct. It might be that the revolute joint is impacting this spherical joint. They might kind of overlap there. Let's suppress for the moment the spherical joint. Let's let this contact exist. And for frictional, let's put 0.1. What if we make the behavior deformable for mobile? Solve. What is this? What is this? Am I missing something? Is this not correctly applied? Should I select the entire bone? Why not? I have nothing to lose. Let's get back to rigid here for the behavior. Save. It wants to get out. It should work. There is some interference, and I think this is the problem. I think this contact, and I think it's too close. I maybe should have left a gap. All right. So I changed for an auto detection value regarding pinball region in this contact. Let's see if the software can solve this contact. Come on. I can move a little this one, a little downwards. Let's see. Control B, part transform, and I'll move it on what axis? This is interesting. Minus X minus Y. Minus 0.025, minus 0.025. And when we're looking in transform, when we're looking in section view, we should see the gap now. Yeah, there is. Ooh, I said there is a gap, but it's not so much gap. So let's leave that contact like this. And solve. After making a cutout, after making a cutout, using the combine operation from SpaceClaim or other CAD software, we need to take into account that the faces, the resulting faces, the mating faces are perfectly touching each other, so they're not optimal for nonlinear contacts, for no frictionless and frictional. They are allowed and are permissible for bonded contacts, but not for frictionless or frictional. We need, as in reality, we need to have a gap. No matter how small, but there should be a gap. All right. I don't want to work with this anymore. Let's unsuppress this. -1, okay. Desperate measures. I don't see overcoming this point, and I think it's a software problem at this moment. It should go after this, and it does not go after this. So I think my solving session is kind of stopping here. Out of curiosity, because maybe this part gives some problems, I was wondering if I can suppress it, reassign the spherical joint to be not body-body but body-ground, Control F, and select these faces. And the coordinate system is this one. Do we care about the Z? We don't care about the Z. It's a spherical joint, we don't care about the Z orientation. So, in principle, we have a revolute and a spherical joint. All right, let's see if it works. This point, we should overcome this point. Oh my god, so it does not go anymore. What should I do? Should I duplicate this simulation? I hear the computer fans revving, throttling very high, and it's clear to me that they are struggling. Let me duplicate this, and maybe I get rid of this error because it just stops here. So now it's not even stopping. All right. Let me duplicate this and see if I can get rid of this error. Stops before solving. Do we have any message from the audience? No. Perfect. All right, let's see with the duplicate simulation if it works. It does not work anymore. This is interesting. What should I do? So what if I drag and drop such a... Do I need to make the setup and the connections again? I don't want to make them again. Let's see if I can. I need to make them again. Let's see if I need to make the joints and the other boundary conditions. We do have these things. Can I drag and drop? Ah, okay, they remain. Only the load. This one, all right. Analysis settings. Let's make a reflection on, I don't know, maybe 5 degrees? 5, okay. Minus 5 degrees. Does it solve? This is my question. I am being kind of optimistic. Yeah, this is new for me. Let's see if I replace it with a transient structure. Will it modify the inner components of the simulation in order to let me solve it? Let's see. It should approach it with a new paradigm. I have a deja vu. All right. Let's make it without joints. Maybe the joints are the problem. Can we make it without joints? Replace with static again. Classic for today. All right. So let's go again for fixed and the load. Instead of force, I like to use displacement. Minus 0.5 or minus 1. Minus 1, why not? Bonded, bonded, bonded. Fixed support displacement. All right, save. So you can see that the software kind of betrayed me in the last period. So let's obtain some results and give it a rest. Next time we will do something with more success, no problem. If it solves at all. Oh, it's solving, okay. So I think I pushed too much on those joints. We'll make them work in a different future session. During these live sessions, I always struggle to have quickly results, and yeah, it's this is the consequence of aiming for the quickest, the fastest, and there are problems, and it's not so much time to solve these problems. They are overcomable. They can be successfully solved, no problem. Only it takes time. Yeah, it takes dozens of hours and days. And let's exaggerate the scale a little. All right, and so in this live session, we have seen lots of ways to edit the geometry, the mesh, the contacts, the solver with analysis settings, imposing stabilization and overcoming errors, and so many tricks. And yes, it's for the beginning it's good. It's good. So let me show elements. It's very nice. Let me also duplicate without results and show only the implant. Yeah, something like this. Thank you all for the attention. We have remarked the proof of concept is there. Maybe offline you show us some results. I'm very curious about the results. Yeah, this is what we could do today. I have similar simulations made, and they were made in the proper time, in dozens of hours and days. So this is what can be done live. So thank you very much for your attention, and I will hear you, and we will meet again in one of the next streams. Thank you. Bye-bye.